Ralph's talk. So the second talk we have today, we've heard a sort of stats perspective on UQ. Now we get an applied maths perspective. So this talk is going to be given by Ralph Smith from North Carolina State University. Ralph?
All right, very good. Thank you. And thanks to the Institute. This is just an amazing workshop. I'm looking so forward to it. So maybe the most important thing I need to do to start with is I've got a whole bunch of examples where I'm going to say we. And we is almost never me. We is a whole bunch of folks I'm working with. I won't be able to do justice to all of them, but I want to point out a number of national labs, Los Alamos, Sandia, Oak Ridge, working very closely with statisticians, Max Morris, my other favorite Max. And one of the things that I want to point to as a mathematician, I'm actually directing a statistics student. And so that sort of points to the synergy that really has to be there between the mathematics and statistics. I hope that doesn't frighten my stat colleagues at North Carolina State too much, but just wanted to point that out. So I'm going to motivate with a couple of large-scale examples. As you can see from the first slide, I actually started with weather, and Jim pointed out that's one of the really big cases where the mathematical models, the statistics came together. I had too many slides, so I pulled it out, but that's one of the things that I love going after Jim is because he covers so many things beautifully that I can point to some of what he said and say, talk to Jim about that. So one of the big initiatives that motivates a lot of what I'll point to kind of the mathematical issues on UQ is an initiative that's supported by our Department of Energy called CASTLE, Consortium for Advanced Simulation of Light Water Reactors. And the mandate is to simulate with simulation-guided experiments next generation light water reactors. So very simply, a light water reactor has kind of a critical component right here where you have neutronics. That's the energy source. Thermal hydraulics, and there's going to be multiple phases which are tried to depict here. And then you also have a lot of chemistry. So it's an inherently multi-physics, multi-scale problem, very, very large simulation codes, and in many cases the measurements are very, very difficult to get. So they talk a lot in nuclear engineering about CRUD. And when I started first working with them, I thought, yeah, I know what CRUD is, stuff on the inside of my shower. But it's boron deposits, and it's a kind of a tongue-in-cheek. It stands for Chalk River Unidentified Deposits, CRUD. And it's extremely hard to measure. You have to shut down the reactor, let it cool, pull it off, and then you realize that the cold CRUD has different properties. So the idea is, can we simulate this? Now, part of what I wanted to do to motivate the complexity of the models is show some of the models. I do not expect people to analyze or understand all of these, but I just wanted to point to some of the complexity of this. So neutronics is modeled by Boltzmann's equation. And in Boltzmann's equation, you get what are called these cross-sections. And they're functions of the energy levels. And depending on the discretization of the energy, you can easily get a very large number of inputs. 100,000 is very, very common. And so in the questions after Jim's talk, the question came up about what do we do in very high dimensional input spaces. These are extremely large, can easily get up into the millions. And what we do is we tend to reduce the dimensionality. Because underlying, there's often a very low dimensional subspace. Perhaps not subspace, but subspace. So I'll point to active subspace construction critical. Codes can take hours to run easily and up to days. Time-dependent surrogates have to accommodate structure, and I'm going to point to the numerical errors. It's often hard to really get a handle on them. My background is numerical analysis, so you think, okay, yeah, we've got all this theory. It's often hard. So I want to point to Mark's talk where he is going to talk about some of the probabilistic numerics, which I'm very intrigued by. And then we're predicting future. It's time dependent, so we're doing extrapolatory or out-of-data predictions, and as Jim pointed out very carefully, model discrepancy is critical here. If we don't understand what's happening with that, predicting in the future is a problem. I pointed to Ronnie's talk. I'm going to be pointing to later talks, and this is a little dangerous because I only partially know. Conveying policy and risk is something that I think in the applied math community we're not so good at, and that's a really big part of that. So that's part of the later. So these are some of the mathematical issues we have to address. Thermal hydraulics. Again, I just don't want to belabor the equations, but we have conservation of mass, momentum, and energy. This is for the fluid phase. We have gas and bubbly. And one of the things that is really critical to nuclear engineers is these conservation laws. There's 3 phases here. And if the codes do not accurately conserve, they've got a problem. So when we started first talking about surrogate models, they immediately shut us down and said, do they conserve? Jim, you probably remember that conversation where I came and said, what do we do? That's still an issue. The surrogates in this case, they're not going to work with them if they don't conserve. They'll go very low accuracy, but they're really locked in on this conservation. You have a lot of closure relations and a lot of parameters. And Jim, you talked about closure relations that are often borrowed. This is the case here as well. So their big CFD code is actually verified and calibrated for flow over a car. And yet they're using it for CFD. And so we have to be calibrating. So calibration is critical. And we often get these random fields. These are infinite dimensional. So this starts to point to some of the infinite dimensional analysis because you have inference of random fields or discretized random fields. Okay, so that's one example I'm going to keep coming back to, and I hope that indicates some of the issues. A second one is ODEs, quite a bit easier, but still very challenging from a UQ perspective. You have 21 parameters, and probably easiest to think about the compartment model. So you have target cells, T1 and T2 target cells. They're born with a rate lambda 1 and die with a rate D1. So in the absence, there's a d by dt, and this font doesn't show very well, so these are all partial differential or ordinary differential equations. So in the absence of virus, they're born and they die. But then you have a viral attack that with an efficiency, think epsilon, is also reducing the population. So it's proportional to the number of viruses and the number of cells. In a perfect treatment regime, epsilon equals 1, and that's removed. And so that's what you're trying to build are treatment regimes where you can take epsilon equals 1, completely remove the viral component, and eliminate the outbreak. That's the goal and the control. Now, a lot of sources of uncertainty on this, and a lot of challenges from a mathematical perspective. So if you look at the viral loads, this is data, it looks like it never drops below 50 counts. And this is a bit misleading because it's not that the virus doesn't drop below it, it's the measurement techniques have a lower limit. And similarly, they have an upper limit of 400, but that one's easy. If you just keep diluting your solution, you can measure the upper, the lower you can't. And so this is a case where your observations are going to mislead what's happening in reality and in the model. You have very correlated parameters. Many times they're not identifiable. And here's a typical response for your immune effectors. So in the first 50 to 60 seconds of this simulation, a large increase, then it goes steady state. So when you talk about sensitivity analysis, you really want to be thinking time dependent, yet that one suddenly gets a little more challenging. And so one of the areas I think that is overdue for more research or warrants much more research is sensitivity analysis for time dependent, space dependent, multiple outputs, et cetera. And I'll show some examples of that. So a lot of places, this is kind of a summary of where I see some of the mathematics coming in on this. So often we have to worry about time-dependent models. We have to accommodate a PDE structure, and that may be conservation. And this is where stochastic Galerkin, commonly known as polynomial chaos, and I'll just kind of state my personal preference. I've never really liked the term polynomial chaos. It goes back to Wiener, who was really studying chaos. And yet it's going to stick. I'll talk about orthogonal polynomials, et cetera, but there it is. Collocation, discrete projection, high/infinite dimensional approximation theory. I'll point to a lot of that work. And then sparse grid techniques for the inherent quadrature that goes with that. So these are some of the issues we'll talk about. We're often doing extrapolatory or out-of-data predictions, and model discrepancy is critical. And I'm just going to kind of come right out. From my perspective, the thing that takes you into that extrapolatory regime is the physics or the biology or the underlying mechanics. And you kind of have to respect that if you're going to build your models here. A lot of look at machine learning to construct closure relations. I'll kind of hint at that. And we get into very high dimensional parameter spaces. This question came up after Jim's talk. In a lot of the applications we're looking at, they look high dimensional, but there's an underlying very low dimensional manifold. And what we want to do is discover that. Compressed sensing, I'll just kind of point to that, and then these nonlinearly parameterizations and so on. So these are some of the issues that, from my perspective, are driving the applied math look at UQ. And the terminology, this is a challenge, and especially notation. So Jim talked about inputs, outputs, quantity of interest. In the math community, especially in controls, we use Q with P being the number, except in the reduced order where we use P with Q being the number. Statistics often is using theta unless there's an angle, at which point it may not, and so on. So one of the first challenges in an applied mathematician on this was respecting the notation and kind of conveying that. And that's just a warning. We've got a lot of young people here. The notation is not uniform. It never will be because we're going across disciplines, and just be aware of that. So I've got a good friend, Bill Browning, who I've known for years, who made the quote, "I've always done uncertainty quantification. The difference now is that it's capitalized." And Allison Wilson, one of my close friends, Jim knows her, now talks about capital UQ versus UQ. And this has sort of taken on this weird life, yet it begs the question, what makes capital UQ maybe different from what statisticians do extremely well all the time? And this came up, I proposed a course on this several years ago, and I very carefully had to justify its existence to statistics because they said, it's uncertainty quantification. Why is it in mathematics, not in statistics? And we were able to make the case through kind of discussion like this, and their students are now taking it. So the question of Bill raised is, what is capital UQ? And I think everybody in this room will have a different answer. Mine is the synergy between statistics, applied mathematics, and domain sciences required to quantify uncertainties in inputs and quantity of interest when the models are too computationally complex to permit sole reliance on sampling-based methods. And even that's really loose, because Jim and all of the statisticians will say, well, we build surrogates, and that's exactly right. What we're doing is we're looking more at things like orthogonal polynomial techniques, sparse grids, high-D approximation theory, randomized linear algebra, and it's all in the context of statistics. So this capital UQ sort of, why do we now have two journals on this? I hope we can kind of answer that. Another quote that I always used to kind of give to Max, and he pointed out that it goes further back, was, "No one trusts the model except the man who wrote it. Everyone trusts an observation except the man who made it." I've seen this attributed to Harlow Shapley. Max's version is computations. Einstein actually made the experiment comment, but Shapley was probably first. So it's a great quote. There's at least one source for it. So where do I see, this is again kind of my perspective on components that go into uncertainty quantification, and there's lots of them. I kind of see the two big ones as calibration and uncertainty propagation. Quantify uncertainty in inputs, quantify uncertainty in quantities of interest. But there's a whole lot of others, parameter selection, model discrepancy, surrogates, and the math is critical in all of those. And there's even kind of a mathy perspective on calibration. So I'll start there because that's kind of the groundwork, and a lot of people say, well, that's just Bayesian analysis. And there's certainly, yes, but we have a somewhat different perspective on it, perhaps. So I said I'd kind of use these two examples to motivate, and I'll talk about the HIV first. There's 21 parameters, but I'm going to focus on 6. So things like birth rates, death rates, these proportionalities, can't measure any of those directly, so we're going to infer them. And if we do ordinary least squares, we just do a point estimate. So I have the model that I'm denoting in F of T and Q, time points Tj, observations, and the parameters vary by 8 orders of magnitude. We know how to deal with that. But what we want to do is see how we would think about this in a Bayesian perspective, and how, in particular, that Bayesian perspective may be a little bit different than what often is done in statistics. So this is not. This is just, everybody knows this. Posterior relation is related to the likelihood, the prior, and a normalization constant. I don't think I need to say much more than that. I just had to have a slide that formalized it. The challenge is we're often in pretty moderate to high dimensions. So for the HIV model, P equals 6 through 23. If you get into, you could go to the nuclear and say, yeah, P equals 100,000, but it really doesn't. We're going to reduce the dimensions. We don't integrate there. I mean, in 6 you can use sparse grids, but we'll talk about MCMC. And here's where I want to again point to later talks. The ABC, approximate Bayesian computing. This is something that is really taking hold in a lot of places. We're looking very forward to that. Bob's talk later. So these are going to drill in on how do we do MCMC in hard problems where we may or may not have a likelihood. That's where approximate often takes hold. So the algorithm that I want to point to, and again, statistical, but it was developed in the applied math community by Heikki Harjo and his group. And it's just a kind of a flip on very, very standard Metropolis. So for those who haven't seen Metropolis, I'm trying to take Dave's admonition of keep this pretty basic. And for those who dream Metropolis, Jim, I apologize. For those who haven't seen it, hopefully this gives a feeling. So the way that this algorithm does is get a point estimate, get a starting point. That's fairly inexpensive. And then you build a jumping or proposal distribution. And quite often you use something that's normally distributed about that initial value. And the covariance matrix, in a sense, quantifies the geometry of it. Do you have correlation? Do you have highly varied parameters? Jim pointed out this kind of correspondence between sum of squares and likelihood. So here, if I have a previous and I decrease my sum of squares, that's good. Here, if I have the negative exponent of that, I'm increasing my likelihood, that's good. And Metropolis says, kind of take a look at that, factor in your prior, and so I have my distribution here, I propose something that's better. That's just basic Metropolis. What delayed rejection adaptive does is two things. The delayed rejection shrinks the proposal if it's not accepted, so gamma might be something like a fifth, and that causes you to accept more. Discover your posterior more quickly. The adaptive is updated as samples are accepted. And the admonition I always give my students is be really careful of adaptive. You've walked away from your convergence criteria. You no longer have a Markov process. You need to prove that. Here what you have is diminishing adaptation, but there's a lot of adaptive schemes out there. Unless there's sort of this proof of convergence, I'm pretty careful with them. Okay, so this is an algorithm that's pretty common in the applied math community, and what do? We construct our chains, we construct our posterior distributions, we construct pairwise plots, pretty effective. And they can be correlated. And the second thing we would do is then, if we have the luxury of sampling, but that again isn't quite the capital UQ I talked about, we'd sample out of the densities for our inputs, make sure that they're independent, and construct credible intervals, prediction intervals. Okay, so for those who haven't seen, a prediction interval is, with a certain probability, where do I expect my next observation? And in a sense, it incorporates uncertainty in the inputs, it incorporates uncertainty in the observations. So from my perspective, that's often a really good measure of the uncertainty in some quantity of interest. So here, I've got some data, I've plotted credible and prediction intervals. They don't have to be Gaussian, we're sampling. The problem is 1 over square root of m. So as a numerical analyst, you're used to hearing things like it converges with order h squared. All right, so h squared says if I decrease h by 2, my error decreases by 4. That's pretty slow, but it's a trapezoid method. Fourth order Runge-Kutta, h to the fourth. Now if I decrease my error by 2, I decrease by 16. That's getting somewhere. Square root of h is terrible. It's really terrible. And we'll see why this is important. It's independent dimension, but it's really slow. So this is where a lot of the numerical analysis is coming in to propagate densities. Stochastic, Lyric, and collocation, discrete projection, is we don't have the luxury of just sampling in many cases. We'll have a budget of 5,000 PDE solves, and I need 100,000 samples. Can't do it. So we use that 5,000 to construct some of the mathematical models, work with those. So I have to show one example, because we got really excited about this about 3 or 4 years ago. Back to the nuclear. This is what we can do with surrogates and so on. In nuclear engineering, they like snake names. No one seems to know why, but they've got Cobra, Hydra, Mamba, and there's all these bad snake names. So we're working with Cobra. It's a subchannel code, a lot of closure relations. And one that they use a lot is the Dittus-Bolter, which is the Nusselt number times 0.023. And part of the relation is not just the functional form, but the numbers. That is part of it. Reynolds number to the 0.8, Prandtl number to the 0.4. And the problem is that's borrowed from single-phase flow and used in multi-phase phenomena. So those numbers are not accurate. But what people will do is employ very conservative uniform bounds. So take twice the parameters, and that would be their uncertainties. And they're going conservative because in nuclear you have to. You have to. So what we did is we got data, we did Bayesian analysis, employed these as priors, flat priors, and here what we have for the first parameter is 2 sigmas about 0.0035. We've added a decreased by an order of accuracy, order of place, similar. So simply using the data and the conservative bounds as priors got a substantial reduction, and we got correlation structure. So then we built a surrogate, and I'll talk about how we build the surrogates for Cobra, and propagated it. So if you use the uniform, you've got about 40 degrees variability. This is operating temperature, which in a nuclear reactor is really, really, really critical. If you assume a Bayes that is just marginals, take the square of your marginals, you get the green, which is about the same. If you use the actual joint Bayes distribution, you got the blue, which reduced 40 degrees to 5 degrees, which we thought, oh, that's pretty cool. Didn't really know what it meant, but smaller. And then we talked to our nuclear colleagues, said they can run your plant 20 degrees hotter, and that's really significant increase in efficiency, which again for the mathematicians seemed pretty cool, but we didn't know what it meant. And then they said that's about $10 billion a year in the US. And at that point we started planning our vacations and retirement. I'm very, very grateful to be here, so the vacations may have worked, the retirement not so much. There's a lot of issues. One of many closure relations, years to take this. However, at that point, Westinghouse, which is one of the big companies in the US, said, we'd like to work with you. They sanitized their codes, they started working with us on this. So this one is one of the places where simply showing the reductions in uncertainty from a mathematical perspective, statistical was great. For the industry, they needed to see not millions, but billions, but then suddenly they're believing in uncertainty quantification. So that was unbelievably exciting. Okay, so one of the areas I wanted to kind of point to current, recent, future research in inference is the random fields. I pointed to one right here. I'm not going to do much on this, but I just want to point out there's a beautiful paper that Andrew Stewart wrote, Acta Numerica. It's this massive, beautiful paper on measure theory. Tan Bui Tan and some of his colleagues have numericized that. Big area of working in infinite dimensional and then discretizing. And I just point out, I come from a controls background, optimization. This reflects a trend that was also there a few years ago, where this discretize then optimize or control versus optimize in infinite dimensions or control in infinite dimensions then discretize. This is the same thing. Do Bayes in infinite dimensions and then discretize. And the philosophy always the same of, can you keep the PDE structure and information for longer? Okay, so there's some current research. I'm trying to adhere to Dave's recommendation and very incomplete, but here's a few of the references. I can give more afterwards. Okay, so I want to talk in the kind of remaining half hour of my time on 3 areas where I see the mathematics playing a critical role and complementing the statistics in ways that I think that they're very, very useful. So first one is parameter selection. We've talked about calibration, uncertainty, but parameter selection. And it's really, really critical for high-dimensional models, or in a lot of these models we have these huge numbers of parameters, most of which are non-identifiable in the sense they're not uniquely determined by data. And I'll point to Bertrand's later talk on sensitivity analysis and visualization. My perspective is that sensitivity analysis is still a pretty open area of research when you talk about time-dependent, space-dependent, multiple responses, etc. A lot of work to be done there. So just a little bit, and I realize kind of equation-y if you haven't seen this, but let's talk through it. For global sensitivity analysis, kind of the classical perspective, goes back to Sobel, is represent your model, and I'm just going algebraic, but you can do this for space and time. And quite often people will truncate at, for example, second order, but you can always represent this if you go up through all the orders. And your coefficients, for example, the F naught is the mean. And you think, okay, that was pretty easy, except it's actually the hardest integration because you're integrating over your entire parameter space. So if you were to say HIV model, that's R23. Nuclear, it's R100,000. So that one may be the hardest yet. And then you get representations. You have a couple of constraints on here, but representations for your first order, second order, etc. And here's where almost everybody until recently said, now let's make the assumption that our parameters are independent. What could possibly go wrong? And if you do that with a couple of kind of orthogonality constraints, you take the variance of your function and you can write it in terms of the variance of these components. And I'm kind of going back and forth between multi-index and single index. It simplifies, and I hope it's fairly straightforward. And then the Sobel indices are simply the variances of the components over the total, or the sum of these. And if they're independent, these things are positive, and they give a really good way of quantifying the contributions of individual parameters or pairs to the total. Really, really beautiful. So here's an easy example that I've done with Billy Oates. It's a colleague of Max's at Florida State, of saying, okay, can we use density functional theory, quantum calculations, to calibrate continuum relations? Really simple. Landau energy is a function of polarization. It's quadratic, fourth order. It has to have these two, but in many cases you incorporate sixth order. It's for lead zirconate titanate, which is a very common and very, very nice, smart material. It's employed in atomic force microscopes. It's in every airbag deployer that's made. And there's a huge emphasis in the modeling of can you replace the lead for the obvious reason, the toxicity both for humans and environment. So a lot of emphasis on molecular and atomic modeling and simulations to custom design materials that are almost as good but without the lead. So if you look at this Landau energy and take the quadratic, the coefficient in front of the quadratic to be negative, so I have an upside down parabola, fourth order positive, so I have this parabola intersecting, and the minimum of this energy well determines atomic positions. Now, fourth order versus sixth order determines the atomic structure. You go from tetragonal to off-center, orthorhombic, rhombohedral. Don't want to belabor that, but this question of is the sixth order term necessary is really important in material science because it drives the structure. Okay, so what we did is we did sensitivity analysis on it. Sobel, Morris, and alpha 1, alpha 11, the quadratic and fourth order terms are an order of magnitude bigger than alpha 111. Okay, so what that would say is alpha 111 is insignificant, sixth order is not necessary. I can fix that and do Bayesian inference and get the same thing, and lo and behold, you don't. You knew there's a punchline coming here. I have no poker face. So what we have here is if we calibrate with all three parameters versus fixing alpha 111 and sampling only alpha 1 and alpha 11, and you get very different answers. And the whole point of this sensitivity analysis is figure out non-influential parameters that can be fixed. So something's gone wrong, our assumptions. And I love these kinds of examples from my graduate students because they sort of think in many cases mathematical assumptions are a nicety and don't have to worry about validating. So what were our assumptions? Well, one of them was that we had independent parameters, and we don't at all. And so the classical Sobel analysis that gives us this, you've blown away your assumptions. You have to accommodate the correlation. It's inherently there. You can extend Sobel analysis to do that and take your variance, but now you get these covariance terms in here. And so the advantage of this is you can do a variance decomposition. That part's great. But now with covariances, you get negative answers. And the beauty when you assumed independent was they were always positive and you could rank the relative contributions. With negative, that's like getting a negative test score. How do you rank that? It's often hard to find this underlying distribution that you're working with here, and it's expensive. So this is one of the areas where when we first started doing this, we always assumed independent because we didn't know the underlying distribution, yet you can get in huge trouble if they aren't, and in many problems they aren't. So what do? One way is to go active subspaces. Accommodates the parameter correlation, very effective, and simply what this is doing is looking for an underlying subspace or manifold of lower dimension where you are uniquely defined. And another really cool area that people have been taking this, and I just pointed to a couple of references, we did this, Paul Constantine, Ten, and Kent, is to then do your Bayesian analysis on this active subspace and map back to the physical space. And you've got identifiability issues, but you can quantify that, and it's really, really neat. I don't have time to talk about it. So let me just talk about active subspaces because this is an area where I think the mathematics has contributed substantially. It's certainly statistical in flavor, but a lot of this is coming from the applied math community. And an easy example, this is out of Paul Constantine's book, is just the exponential of 0.7 times a parameter, 0.3 times a parameter. So it varies in one direction, and there's no direct variation in the other. You have a 1D active subspace, and that's what you're looking for, is back out that subspace. So I always like thinking about the history on this, and Jim, thank you for the history on yours. I don't do as good a job, but this active subspace is often attributed to Russi in applied mathematics in 2010. Okay? Really recent stuff. Except it's exactly the same as identifiable subspaces, and you can reference that and read in 1977. And if you're linear, it's the SVD and QR, which I don't even know. These are some early references. There's a beautiful review paper by Stewart. So I always kind of point out this is taking this huge line of credit in certain areas, and that's fine, but it goes back to controls from a long time ago. If you're thinking about subspaces, and again, linear is classical. So how do you back these out? Well, you're already thinking, okay, if it's linear, I do an SVD or QR, and that's exactly right. The question is, how do you take them high dimensional? And that's a really, really interesting question. But let's go for nonlinearly parameterized, because almost all of our examples are nonlinearly parameterized. Partial differential equations, these are coming in as coefficients. Only rarely do we get a linearly parameterized problem, and I don't live right enough to do that. I always get nonlinear parameterized. So what do you do if you've got nonlinear? You linearize. All right, so I take some kind of a gradient. That's a problem because often we don't have them. Form this outer product and partition the eigenvalues. Look at the eigenvalues, and the easiest way to think about that is look for a split in your eigenvalues. Okay, and I'll show in the next slide. This is equivalent to SVD if you look at it right. So you've got some really powerful linear algebra, but you look for partition the eigenvalues, say 10 to the minus 8, 10 to the minus 10. Bigger than that, we take the basis in our eigenvectors, and that's our active variables. Smaller than that, inactive. All right, so it's very natural, and we've all done that in linear algebra. Take the SVD, look for the singular values that are significant, take the corresponding singular vectors, that's the basis for the space. This is taking it to the nonlinear version. Now, construct this outer product in this. This is a problem. We almost never have these, but so far it's mathematics. I can write down what I want. So how do you evaluate this? Well, we do Monte Carlo at this point, but we have to keep these fairly small. So we draw independent samples from our distribution, and that one, you say, well, you just said you don't know the distribution. We get a point estimate, and this seems to be much less sensitive than the global sensitivity analysis. So there's this conservation of difficulty thing. Yeah, there's a distribution there. It's less sensitive, and a point estimate usually does fairly well. Evaluate or approximate the outer product, and here's where you take your singular value decomposition. Unless you're really high dimensions, and this is again where some of the math comes in, and form your active subspace. So in principle, this is all in Paul Constantine's book. Siam came out a couple of years ago. There's a lot of work. Miro and Clayton Webster, who unfortunately couldn't be here, have a beautiful paper on this. There's a lot of work on this. There's a couple of the references. I can give you more. What are the researchy issues? We often don't have gradients. Now, in neutronics, we have adjoints, but they may not be so accurate. So we've got to do gradient approximations. These singular value decompositions are often very high dimensional, millions. So recent research, how do we do this for codes that don't have gradients? You'd like to say finite differences, but they don't work well in the interesting places. So we've been looking at kind of initialization algorithms. This is the work with Max Morris, Morris indices, etc. So researchy stuff there. And then there's a very heavy reliance on randomized linear algebra. And I'll point to the Halko-Martenson-Trope Siam review paper. The idea, embarrassingly oversimplified, is if I take independent samples, I'm getting new information with a certain probability. So by taking these independent samples, I'm getting new information, and I can back out the underlying structure cheaply. I don't have to go up into the millions. Often I can get it with a factor over the subspace. So that's what we're relying on. So how does this work? Nuclear. Input dimension was 7,700. K effective is really simply, it determines whether a reaction goes forward or backward. And so for them, that's everything. Is the reaction shutting down? Is the reaction going forward? What's the magnitude of K effective? A lot of materials, a lot of reactions, 7,700 inputs. And in neutronics, that's not really big. They'll go with high, but it's not 100,000. And for math students, there's some really annoying realities with this. One is you're getting cross-section libraries. So they have these beautifully libraries. They're all binary. So when you start talking about doing perturbations, which everything is based on, or even samples, you've got binaries. So then you have to work with some kind of a translation from binary to floating point and back to binary. That was about 6 months for Allie going in her dissertation of be able to translate. So these are some of the realities that are hard on these problems if you're really going to work with the applications. And so what does it do? Input dimension 7700. We were able to, this one we do have adjoint capabilities, but you have to be careful of the accuracy. So you see that, and analytically you have eigenvalues of 0 and 1. This is a really nice test problem because you know the eigenvalues analytically. That's why the nuclear folks love this. And it's a real problem for them. So you go from 0 and you're down you start from 1, get down to 0 basically in a couple of iterations with both algorithms. And there's a variety of metrics, the gap-based, error tolerances, PCA. But the bottom line is you get a 1D active subspace in a 7700 dimensional space. And this one they know they're not always this low, but that's the kind of structure we're often looking for. In real problems, we'll get down to 15 or 20 from 100,000. So you're looking for a very low dimensional subspace in this high dimensional problem. One of the warnings that I always take away is converged adjoint solutions are hard to get in many cases. They'll talk, yes, we have adjoints, and they do. Getting them to converge is not so easy sometimes. So that's the types of things that we're looking at with the active subspaces. Can we find a very low dimensional subspace or manifold? And then if you're doing Bayesian inference there, we would do inference on, in this case, the 1D, but then it raises the question, what happens when you go back to the physical problem? And you have to have some kind of sensitivity measure to talk about which parameters you're going to inform and which you won't. And there are measures to do that, but those are some of the issues. Okay, that one is kind of what I consider a new area in which applied mathematics has contributed substantially and augments the statistic. More classically is surrogates. And Jim set the tone beautifully for this in his talk. So I'm not going to spend too much time on the statistical perspective and be able to jump on. Go by a lot of names, interpolation, regression. Jim talked a lot about Kriging and Gaussian process. Tony O'Hagan is going to talk later about that as one of the experts. I will not. So I'm going to talk about the orthogonal polynomials. So what we have is we have a high fidelity model or data, and high fidelity for me is model drawn on a whole bunch of coffee like I was this morning. And then you've got some kind of low fidelity interpolatory or regressive model, which I'm denoting in blue, and I'm going to call it F sub S of Q for surrogate, and I have a set of measurement points. And what you do with this high fidelity model Y equals F of Q with evaluations, or this low fidelity statistical model, determines the various methods and the attributes of those methods. One of the things that my students always get nervous about, they said, why are you looking at a statistical model for a numerical model? It's very convenient, it applies to data, and in some cases with some of these models there is some stochasticity to them. So what do we do in the numerical analysis community? And this very naturally reflects a lot of the spectral methods that go way back to, David Gottlieb, Steve Ortzag, very classical. We represent our surrogate, I'm going to go kth power, in terms of coefficients and basis functions. Same thing you would do with Gaussian process. However, our basis functions are now orthogonal polynomials that are orthogonal associated with a certain probability density function. So if you're normally distributed, we use Hermite polynomials. If you're uniformly distributed, we use Legendre polynomials. There's a whole class of what are called ASCII polynomials that will generalize this somewhat. But one of the things that Jim pointed out, this is not a panacea by any means. Suppose you're doing inference with general Bayesian inputs, you may have some issues here. But our basis are these orthogonal polynomials. Now, the orthogonality buys you a lot. So I've got my representation, and the first one of these is just unity, so the expected value of that, and I went to the capitals to indicate random variables here. Expected value of this is 1, and then through the orthogonality, if I look at pairs of these, expected value of phi j, phi I, they're all 0 except when I equals j, and then I get these gamma i's, and in many of these common cases, you can write down formulas analytically for those. All right, so the orthogonality says we know a lot about the individual expected values, and more importantly, we then know a lot about what's happening for our quantity of interest, the representation. So the expected value is simply alpha naught, the first term, and the variance terms on these are determined in terms of alpha k's, and the gamma k's, which are often known analytically. So this is a big deal. In principle, if I know my alphas, I know the moments for my response, for my quantity of interest. And this is used extensively in uncertainty propagation, Sobel-based global sensitivity analysis. It's a beautiful result. The catch is, how do I determine these coefficients alpha? And that's what determines a number of the different methods. So how do you determine these? Polynomial chaos expansion, PCE, often is applied to Galerkin techniques. Project down, use a Galerkin representation. This typically is intrusive. You have to go into the code and be forming inner products. I'm not going to talk about it for that reason. Okay? Theoretically, you've got very nice convergence properties. However, it's intrusive. Non-intrusive is non-intrusive, hence the name. I know it by discrete projection. That's more the classical numerical analysis term back to Gottlieb and Ortszag. I'll talk about collocation, and then I wanted to point to some of the regression-based methods with sparsity control. All of these we're using because they treat the code as a black box. We do not have to go in on the code and modify it. I have colleagues who will say, well, with exascale, we're going to have to modify the codes anyway. We might as well get started. True, but I'm not there. So I'll talk about the latter three. All right, so the whole question is, how do I determine these coefficients? And then once I know them, I know a lot. I've got some pretty powerful properties in some cases. So non-intrusive PCE or discrete projection says, take the weighted inner product of this. So I'm going to multiply times the psi I. The weight is the density. And then I use the orthogonality of those. And so I get psi I times psi k's. That's either 0 or 1. I keep the ones where it's 1, and I can write my coefficients alpha k as 1 over gamma k, and then the integral of my solution times basis functions. Okay? Really nice, except it's a high-dimensional integral. This is over the dimension of the parameter space. We're doing quadratron here, which says evaluate these at quadrature points QR with weights. All right, so how do we do the quadrature? If it's low-dimensional, and I'm not going to define that, but it better be less than 5 or 6, we just take 1D rules, Gaussian, trapezoid, whatever your favorite is. Trapezoid's not so good, but Gaussian, etc., and just tensor them together. Start putting them together in different dimensions. For moderate dimensions, it's the Sparshas-Smoliak techniques. And high-dimensional, Monte Carlo, or QMC. And QMC, Jim pointed a little bit to some of what you get with the space filling, sampling, etc. That one's probably the best of these. So it comes down to evaluating these integrals, or how do you choose your points. Regression-based with sparsity control, you're solving an optimization problem. You're just minimizing the difference between the solution and our expansion, subject to L1 constraints on our coefficients. And so you've got sample points. This matrix is just basis functions evaluated there, solution evaluated there. You might say this is really hard, but there's some pretty good software out there. SPGL1 is a MATLAB solver for large-scale sparse reconstruction. For moderate dimensions, this is fairly tractable, and there's some software to do it. Collocation, you can make it look like Galerkin, but it's collocation. It's somewhat different. And so for a collocation model, here I'm going through a set of points. What I would typically do is represent my surrogate in terms of the solution, the model evaluations, and Lagrange polynomials. And this is a lot of terminology, but the Lagrange polynomials are built so that when I evaluate points, I'm either 0 or 1. They're guaranteed to be 0, 1. The other thing is if I add a point, I just simply add terms. Okay, so you say, okay, I went from, Jim, I love your example of 9 to 10. So I'm just going to use those numbers, totally different context. If I add a point, I simply add a term, and I don't have to reevaluate everything. And so what that says is if I take my collocation surrogate and evaluate, that is my high-dimensional solution. Okay, so it's collocation theory. Again, you can pose this in a Galerkin framework, but it's somewhat different. There's the other way you'd build this. So this is all algebraic. How do you do this in a PDE? I'm not going to belabor this slide because it's a lot of squigglies, as one of my friends used to say. But thermal hydraulics, you can write this as an evolution equation, time derivative, operator, and the easiest case is think heat equation, where I have one parameter, and I write the weak formulation of that, multiply by a test function, integrate by parts, look at the weak formulation, I have a response. I write down my representation. Here you would be doing a finite element representation, and you do the same thing. So this is a very natural framework for PDEs, and that's where it's gained, I think, a lot of the traction in our community. Is very natural. You can take your finite element codes and work with this. So the question comes up, how do you choose your points? Everything comes down to how do I choose these points? I'm doing quadrature points, etc. So one of my favorite functions, I never realized the beauty of this when I took undergraduate numerical analysis, is the Runge function. 1 over 1 plus 25q squared. What could possibly go wrong? So you sample this at, I think this is 11 points, and it looks like octopus. So as a numerical analyst, what do? You increase the number of points. Obvious. And this is supposed to be on a scale of 0 to 1. You increase the number of points, and you're now on a scale of negative 80 to 20, and you've got a problem. And the problem is at the endpoints. So the point of this is you don't want to use uniformly sampled points because you've got this Runge phenomenon. So let's use cosines. These are zeros of certain polynomials. And this looks slightly better, and this looks great. So the lesson to be taken away on here is, first of all, we don't use uniformly distributed points typically. We can go for zeros of certain functions, these, or randomly sampled. But typically, that's the first lesson on this is we don't go uniformly sampled. Second question when you're choosing your points is, how do I avoid the curse of dimensionality, or we don't avoid it, how do we push it back? And this would be the sparse grid techniques. So tensor grid, here's a 9 by 9. Don't have to fire up anything to say 2D, that's going to be 81. And here's the same sparse grid with 29 points. And this again goes back to Smoliak. And you start to see the improvements. 10D, I've got 3 times 10 to the 9th versus 1581. So this is why people in moderate dimensions are very, very interested in sparse grids. There's MATLAB toolboxes for this. There's adaptive sparse grids. I won't do it justice. It's a big deal. And Max, everything I don't talk about, I'm going to tell you Max is going to talk about. So you may talk about the sparse grid errors. This comes down to just, if I have a function that's, say, continuously differentiable alpha, or continuous alpha times, in 1D, I have Newton codes are relatively accurate. The problem is I increase my dimension, I lose accuracy. Gaussian is more accurate. Sparse grid pushes this back a little bit, but you always have a dimension p coming in here. That's the problem is with the curse of dimensionality. You can avoid that with Monte Carlo. There's no p in this, but you have very slow. And I had a student several years ago gave a beautiful talk on this, talking about for high enough dimension p, monkeys throwing darts will beat our best numerical methods. Oversimplified, but sooner or later that p is going to come in. So what are people doing yet? Quasi-Monte Carlo techniques, there's a present SAMSI program on this, and I'll point to later talk that Henry's giving on some of the sampling. Jim pointed to some Latin hypercube. So there's a lot of work still on how do we choose the points, the quadrature, to push this dimensionality curse back a bit. Okay, so quick example. This is a SIR cholera model where I have susceptible, infectious, and recovered. And the way cholera works, I'm going to word this kind of carefully, is waste from infected people generate cholera bacteria, which then infect susceptible. Highly infectious can kind of devolve to lowly infectious, but there's a simple model for it. It's very similar to the HIV. It's a compartment model. And here are the parameters for this. And you'd ask, which one of these parameters are the most influential? Okay, it's time dependent. So we looked at all of these parameters. It's moderate dimension. We used 2 of the orthogonal polynomial techniques to represent this. We used sparse grids. And what we found was gamma is the most influential. Here's time-dependent sensitivity analysis. Here's a comparison of various techniques. So the recovery rate's the most. Drinking rate is next to there. Carrying capacity, etc. So illustration of that, if people recover really fast, the susceptibles don't have time to generate the bacteria, and you don't have as much of a problem. Next one is how quickly the bacteria infect the susceptibles. less so is the infection rate, and then the final is the carrying capacity. So there's an illustration of use. I will go through this fairly quickly. Max is talking about this tomorrow. Julia's talking about aspects of this. This is an embarrassingly incomplete set of references. Max has done a lot of work in this. Babushka, I don't have time to do justice to everybody who's worked on this. Get the slides from me. Switzerland book, Spectral Methods for Uncertainty Quantification, a good place to get introduced to it. And if you're talking about sparse grids, Bungartz and Griebel, two of the huge leading names in this. A lot of people have worked on it. And then Clayton and some of his groups, as well as others, are doing really nice work with compressed sensing. So get the slides, and again, this is embarrassing incomplete, because I want to spend just a couple of minutes on the one I can't really say a whole lot about, which is model discrepancy. And I'll just spend a couple of minutes on this and then wrap up for questions. So model discrepancy. All models are wrong, but some are useful. So how do you show this? We've got a Euler-Bernoulli beam equation, fourth order, 7 parameters, 32 states, typical statistical model, and we did a fit. We, being my postdoc, spent many, many days getting a fit. And in the time domain, it looks pretty good. So I've got data and model, looks pretty good. Frequency domain looks really good. I don't have IID observation errors. Jim talked a lot about the Kennedy-O'Hagan framework for identifying that. But what could go wrong if you don't have IID observation errors? You build your prediction interval, and you're close. The gray is the prediction interval, but you're off. You've got a phase shift going on here. So you'd say, well, it's close, and that's true, but 95% prediction interval is not correct. And the reason is you've just totally wiped out your statistical assumptions. You have model discrepancy here. Jim talked a lot about the Gaussian processes. There are control approaches, but you have to know the future. And again, our problem is we are trying to do extrapolatory predictions. So Bob Moser and his group will say, pick the parts of the models you trust, the conservation laws, and don't trust. Work with those. And that makes a lot of sense. The physics is what carries you forward. I'm going to do a plug for a SAMSI program next year. We've got a couple of folks, Jim and Bruce Pittman, who are involved on this, on model uncertainty. It's a big area. And if you're doing extrapolatory predictions for all the reasons that Jim also mentioned, you've got to get this right. What we did is we said, well, let's optimize our calibration interval. Went a little bit later where the model is doing a better job, and that worked. But this model discrepancy is hard, and we've got to get it right when we're doing extrapolatory predictions. So let me go ahead and conclude with some thoughts. For me, capital UQ is this very natural blend between applied math, statistics, and whatever domain science you're working in. And for a lot of the reasons Jim also pointed out, we really live in a Bayesian framework. For the reasons I showed, as well as experimental design, model selection. A lot of the mathematical aspects, you've got the orthogonal polynomial base, sparse grids, high dimensional approximation theory, active subspaces, and there's a lot of software that's getting pretty mature. MATLAB, Sandia package, Python, R, for materials NanoHub. And the place I'll end on this is one of my favorite quotes. Prediction is very difficult, especially if it's about the future. I first would have attributed that to Yogi Berra. He said it at the same time as Niels Bohr, but Yogi did not develop the theory of the molecule, so Niels gets it. And it's a Danish proverb, so I have to give it to Niels, I believe. So let me go ahead and conclude there.
Okay, questions, comments?
Yeah, Max.
Who's Yogi Berra?
You know better than I do on that one. That's why I go with Niels Bohr. I can see the level of where my talk took this, the intellectual level here. So, yeah.
I'm going to be a little bit controversial, I think.
Absolutely.
Is that okay?
I think we have no choice. I just fastened my seatbelt.
So sparse grids, you have these big holes in sparse grids, and
Right.
the reason they're like that is because you're trying to get exact quadrature for certain polynomials.
Absolutely. Absolutely.
So first of all, they're sparse, they're not space filling, you know. But there's one case in which you would be space filling. If you were fitting a Fourier kernel, as opposed to polynomial, the solution would be equally spaced. and would be a space filling. So there's this tension between what the statisticians are doing in terms of using it in interpolation, and my slight criticism is that you're trying to maybe sell into the interpolation area what was actually classical orthogonal polynomial quadrature.
Yeah.
That's my...
Oh,
that's
absolutely,
my
and I'm glad you brought that up because they're certainly not a panacea. For certain classes of functions, and with certain regularity, they'll do very well. When I did propose some of this to the nuclear folks in thermal hydraulics, they said, what about a shock? And if you've got discontinuities, if you have any number of places where they're violated, you're absolutely right. So for certain classes, they're great. I would not rely on them only. And one of the mantras that I keep kind of coming back to is verification, verification. I would try and be getting at least 2 different methods to give the same answer. But no, you're absolutely, there's a large class of functions where they're absolutely not the right choice. Yeah, Max.
I just want to make a comment on that, and that is that Fourier or any spectral basis is no better than sparse grid basis in that respect. And the Fourier basis also needs smoothness, or else you get into serious trouble for the same reason.
Absolutely, absolutely. So, and I was talking about spectral methods. People have looked at kind of finite element-based approaches to work with some of this smoothness. But yeah, what I was pointing out was kind of the classical way that people first started thinking about this, based on the spectral theory. But anytime you lose the smoothness, you have to rethink it. Yeah.
For the model discrepancy, when you don't have stationary errors, would you look to time series models like Arman, Nariman, Garsh, and this kind of thing? Would you recommend that?
Yeah, no, and in some cases, we've had students and postdocs who've done really nice kind of time series expansions to work with model discrepancy. The place where it always gets so hard is when you're doing extrapolatory predictions. And when we're doing that, I just keep kind of coming back to this mantra of it's the physics of the biology, the underlying process that takes you into that extrapolatory regime. So we have to figure out the parts that we really trust there and then improve the parts we perhaps don't and get bounds on them. But yeah, for certain applications, you can certainly do a kind of a time series or other data-driven approaches for that, and they do very well. It's as soon as you start doing the extrapolation that you really want to try and preserve as much of the structure as you can. And the problem is it's always problem dependent, but this figure out what parts of the model you trust, figure out what parts you don't trust, and try and work with that, to me, is kind of the easiest big picture approach.
Yeah, so in the beginning you said something about sometimes conservation laws are really important, but somehow I must have missed it, but I didn't see you coming back on that, on how to build surrogate models that...
Yeah. So I made the point in the nuclear, and this is the conversation I've had with Jim, of in multi-phase flow, the conservation is just critical. Mm-hmm. So what they did, Cobra, I mentioned the snake named Cobra.
Yeah, sure.
What they did is they built a very, very low accuracy model that conserves. Okay. And so what they'll do is they'll build often projection-based models that conserve. And so what they did is pins are about 1 meter apart, that's the delta. And so it's very, very low accuracy, but it's built to conserve. And so that's the approach that they and other people that are looking at this. Jan Hesthaven is doing a lot of work at Zurich of basically structure preserving surrogates, and you always have to kind of build it into your basis somehow. Okay. They built it into the basis, but it always has to come into the basis in some manner. Mm-hmm. Mass is not too hard to build into a basis. Momentum and energy a bit more challenging, but that was their approach.
Okay, so let's thank Ralph again. So we now have our poster blitz. So can I just ask, I think we should have 11 poster presenters.